Hi, today we're going to be covering section 3.2, which is polynomial functions. And their graphs. So first we have to define what a polynomial function is, and we have talked about these in the past. So the definition of a poly is any function that is of this form. Okay, so it's of this form where your ANs are reals and your exponents, your n's, are positive integers. Okay, an example of a polynomial would be a polynomial function would be something like this. Okay, this is an example of a polynomial function. Another example would be this. Notice here we have real coefficients, square root of 5 and pi. Both of these are polynomials. Things that are not polys are things like this, because this has a non-integer exponent. Okay, and there's other examples like that where the exponents are different. Okay, now the thing with polynomials that we're going to be talking a lot about in this section is that we're going to be talking about leading coefficients. Okay, and leading terms. Well, a leading coefficient is just the coefficient in front of the leading term. In these examples here, the leading coefficient would be this. The leading term is the whole term here. So the leading term is the term with the highest exponent. Okay. So here, this is your leading term. Here, this is your leading term. In this definition, this is your leading term. Now, don't always expect your leading terms to be in front. You can have them arranged so the leading term could be anywhere, really. So in this example here, the leading term is this guy here, and the leading coefficient's -5. Okay, so those are things we have to talk about. You also will mention constant terms. Constant terms are the terms without any variables. So here's your constant terms. Okay. All right, so let's continue now. When it comes to graphing polynomials, one of the main things you need to know is that polynomials are smooth and continuous functions. Okay, so all polys are smooth and continuous. So what that means is smooth, meaning it doesn't have points. So a non-smooth function might look something like this, where it's got points. Continuous has to do with it doesn't have gaps. So when something's not continuous, it might come to here, stop, and then go up. Okay, so this is not continuous, and this is not smooth. So in general, polynomials will look something like this. Okay, they'll be smooth and continuous. Okay. So the first big thing to know when we're talking about graphs of polynomials is we want to know what their end behavior is. Okay, so what is the end behavior of a poly? And it is something that you can easily just look at a polynomial and tell what the end behavior is. And it has to do with the leading term. So you're going to find the leading term and you're going to find the exponent on the leading term. So you're looking for the exponent on the leading term. In our definition, the leading term was the an xn, n is your exponent here. So we're looking for the exponent on the leading term. Okay, and what we want to know is the, okay, and we're also looking for the leading coefficient. So we're going to create this table here. Okay, and so we're going to have odd exponents or even exponents. Your n's can either be odd or even, and then your leading coefficient is either going to be greater than 0 or less than 0, okay? Now, if it's odd, your end behaviors are going to be opposite. So what I mean by this is when the function goes off, it's going to have some humps here, some hills, and at some point it's going to stop switching direction. It's either going to go up or down. So if a function is odd and the leading coefficient is greater than 0, then on the left side it's going to be going down, on the right side it's going to be going up. Okay, so example of that would be here. So here's an odd function. So here's an odd function. It's some f of x to the x to the third plus other stuff. So it's an odd, not an odd function, it's an odd leading term. So the odd leading term, it's in behavior, it's going down on the left-hand side and it's up on the right-hand side. So again, my correction, it's odd leading term, not odd function. We talked about those later and we'll mention them later today. If the an is less than 0, then you have the opposite behavior. It's going to be going up on the left-hand side and down on the right-hand side. So example of that, if we looked at our function here, so f of x equals negative x third, so your an is negative, it is going to be going up this direction and then down. Okay, so it's up this way, down that way. Okay. Now even functions, their end behavior is always the same. It's either always both going up or both going down. So if your leading coefficient is positive, then they're going to both be going up on the end behavior. If the leading coefficient's negative, then they'll both be going down on their end behavior. So an example of those, coming back here, is if we have f of x equals x squared. It's a simple, has an even, okay, an even leading exponent, and it will look something like this, okay. Notice it's positive, it's going up on both ends. However, let's say we have a negative x squared, then it will look like that. It'll be down on the end behavior, okay? So those are the end behaviors. And we find those by looking at the leading term. And when we look at the leading term, we're interested in the leading exponent and the leading coefficient. And the rule is right here. So let's look at some examples. Example 1. find the end behavior of this function. Well, the leading term, what is it? It's right here. It's an x cubed. So the exponent is odd. And the coefficient is greater than 0. It's a 1. So it's an understood 1 right here. So our coefficient is greater than 0, and it's odd. So we're going to have this behavior up here. So we know the end behavior, it's going to be going down this direction and then up this direction. Okay. Now we don't know what's going to happen in between. We do know you're going to have probably some switches in directions because of these terms over here. So I'd hypothesize it's going to look something like this. Okay, and we'll figure out how to find those things later, the middle behavior. But right now we're just looking at the end behavior. Let's look at another example. Well, here's our leading coefficient is 1, our leading term. Leading exponent is 4. Okay, so we know that our an is greater than 0 and our n is even. So we're in one of these cases here where it's going to go up. So I know our end behavior is going to be up on both ends. Okay, now maybe the inside behavior, it could look like this, okay? Or maybe it could look like come down, up, down, and then back up. Could like any of these. You could add as many humps as you want. There is a rule, we're gonna talk about this rule in a minute, of how many humps you can have here, how many switches of turns of directions, okay? And we'll go ahead and deal with that now. So I'm talking about turns or changes of direction. Excuse me. Okay, when we have a function that looks like this, we know it's end behavior. We know it's even exponent here. We know the coefficient is positive. So we know the end behavior, it's going to be up on both ends. The question is how many humps can you have? You can have one less hump than the exponent on the leading coefficient. So here, we can have one less hump than 4. So we can have 3 humps, 2 humps, 1 hump, or no hump. Okay? Now, let's use a little bit of logic here to figure out which of those is actually possible. Since it's ending in the same direction, we can have 1 hump, okay, 1 change in direction. Okay, we can have 3 humps, or 3 changes in direction, so here, here, and here. But notice you really can't have 2. If you try to have 2 changes in directions, notice you're going to go down this direction. You can't get back around to going back up without another change in direction, which gives you 3 instead of 2. So on your polynomials that have an even exponent on the leading term, they're always going to have an odd amount of change in directions. And your functions where the leading coefficient is odd, they're always going to have an even amount of changes direction. So here, since it's negative, since our coefficients, our leading exponent is 3, and the coefficient's -3, less than 0, we know that it's going to be going up on the left end and down on the right end. Okay? Now we know it can have, in this case, none. It can have no changes in directions. It could just be something like this, all right? Or it could have, so that's 0. So you could have 0 changes in directions. Or you can have 2, like that. 2 changes in direction. You can't, however, have 1. There's no way to have 1 change in direction and end up going, because you have 1 change in direction, you can't end up down here. You'll end up back up here, which means it's in one of these even categories. So here, these will have an even number of changes, less than 3. Okay, this one up here, it'll have an odd number of changes, less than 4. Now, can we go any further? Can we extrapolate what's actually happening in the center here? We know the end behavior, but can we figure out what's going on in the center? Well, we do have a few more tools we can use. Okay. The tools that we can use is we can look at the zeros of a polynomial. So what are the zeros of a polynomial? The zeros of a polynomial are where the polynomial crosses the x-axis. So when we're talking about what's the zeros of the polynomial, we're really asking, is it either crossing or touching? Could be touching as well. Crossing or touching the x-axis. How many times does this poly cross or just touch the x-axis? Okay, so visually, okay, this right here, I can tell just looking at this graph that this is the leading coefficient will be, the exponent will be even, and the coefficient will be negative because it's going down on the end behavior, and they're both going the same direction. So I know it's even. And I know that the leading coefficient is less than 0. Okay? But if we look here, it's crossing 1, 2, and then just touching a third place. Okay? So we can actually find these if we can factor. Now, this can be difficult. Some of these are not factorable. That doesn't mean that they don't have 0 polynomials. It just means it's not going to be an integer. It could be real numbers, which you're going to have to use Pythagorean's theorem or various other theorems. So how do we find the zeros of a polynomial? Well, let's just look at an example here. Here's an example of a poly, and we want to find the zeros. We want to find all places where it either crosses or touches. Well, we're going to have to use our skills at factoring here. We notice this has 4 terms, and all that we really know how to do with 4 terms is factor by grouping. And this is one of those cases where that will work, so we'll go ahead and do that. We'll put our parentheses in. I'm going to rewrite it first. All right, I rewrote it, put the plus here. Remember, every time you have a negative, you need to include it inside the parentheses and put a plus outside. Now, We factor by grouping. What can we factor out of these two? Well, we can factor in x squared, so we'll do that. Okay. Now, what can we factor out of these two? Well, whatever we want to factor out, we want it to equal x plus 3. So we're going to factor out a negative 1. If we factor out a negative 1, we'll have x plus 3. Okay. And then we'll regroup. Okay. And then we'll ask ourselves, can we continue to factor? And we can. We know what the factor of this is, all right? This is the difference of squares. So we can factor this directly using our memorized equation, which is x plus 1, x minus 1, and then x plus 3. So we now know that it has 3 zeros. What are the zeros? So the zeros are negative 1 from here, positive 1 from here, and negative 3 from this term, or factor, this factor. So our zeros are x equals negative 1. You set this equal to 0. You get negative 1. Here you get positive 1. And here, when you set this factor equal to 0, you get negative 3. So on a number line, if this is 0, this would be negative 1, negative 2, negative 3, 1. We know that it's crossing at negative 3. It's crossing at negative 1, and it's crossing again at 1. Okay. We also know, since this polynomial, the leading term is a cubed, we know that it will either make 2 turns or 0 turns, okay? And judging that it crosses 3 times, we know it's going to make 2 turns. Okay, we also know that since it's positive here, the leading coefficient is positive, we know it's going to start down here, and then it'll end going up here at the end behavior. So we know it's going to cross at negative 3. It's going to have a change in direction to get back to negative 1. It's going to cross at negative 1, have another change of direction, cross at 1, and then go back up. Now we don't know the heights of these and where the relative mins and relative maxes are. Okay, this would be a relative max here, this would be a relative min. I don't know what they are here. And in college algebra, we won't really learn how to find those. In calculus, you will learn how to find the relative mins and relative max by using the derivative. But that's outside the scope of this course. But just letting you know, you can find these mins and maxes and figure out exactly where they cross, where they are on the x-axis. Like maybe it's at negative 2, etc. But we won't be learning that here. So, but we do know it'll look something like this, okay? So we know it has 2 changes in directions on this guy. And I also know it's got a relative min in here. In between negative 1 and positive 1, there's some min, and up here there's some max in between negative 3 and negative 1, relative max, relative min. Now they're not absolute because you go off to negative infinity this direction, positive infinity this direction. Okay. All right, now let's continue on with this. Look at another function. Here, I'm going to give you one that's already been factored. Okay. Now, first off, we want to know what the end behavior is. Now, we need to know what the leading coefficient is and the leading exponent. We could FOIL this all out and write it all out, but then we'd have to refactor it and get back to here, or just remember this. And we can go ahead and do that. But we're really only interested in the leading coefficient. So to find a leading coefficient and leading term. So to find that, I'm just going to take this x squared, multiply it by, this is understood to be an x squared. If we were to FOIL this out, it would be x squared minus 6x plus 9. So it would be another x squared and then a single x. So x squared times x is x to the 5th. We know each one of these has a coefficient of 1, so 1 times 1 times 1 is 1. So we know when we were to FOIL this out, we would get a 1x to the 5th, okay, plus a bunch of other stuff, which we are uninterested in, okay? So this tells us here that the leading coefficient's positive and the exponent is a 5th power, so it's odd. So we know it's in behavior since it's positive, is we know it's gonna, again, the odds, it's gonna be down here and up here, okay? And since it's 5th, we know it can cross or touch the x-axis, cross four times, 3 times, 2 times, 1 time, etc. Now, if you just touch, that doesn't count as a cross. If you're doing all crosses, okay, so what does this do here? We know here, we know it's going to cross at 0 or touch at 0. We know it's going to cross or touch at 3, and we know it's going to cross or touch at 1. So 0, 3, and here's 1, 2. So we know right here. Okay, now, how do we know whether it crosses or touches? It has to do with what they call multiplicity of the factor, okay? And the multiplicity is how many times the factor occurs when you factor out the polynomial. This x equals 0 occurs twice because there's an x squared here, okay? X plus 3 occurs twice. So if the multiplicity of the factor is even, so if your multiplicity is even, okay, then it just touches. Okay, it doesn't actually cross, it touches. If the multiplicity is odd, it crosses the x-axis. So we know here, this guy, since it's even, and this guy, since it's even, it touches. So it's just going to touch. Okay, so it's going to touch. Okay, it's going to come back. So it's going to look like that here. Okay, multiplicity of 1, though, however, is odd, so it's going to cross. So it's actually going to cross at 1. And then and come back down and just touch at 3. Okay? So notice here we have 3 changes of direction. But also touches or crosses 3. So last time I was talking just about crossing. Okay, here crossing and touching are slightly different because it can, touch is kind of like, normally a touch would take 2 places. So you can't actually get it where it touches or crosses 3 times, even though we know this is a 5. So the last ones, we expected 5 to get an even number of crosses. And that's if you don't have multiplicity. Okay. Look at another example here. we look at this function, we'll notice that this is a square here, this is a cube. So this factor has the multiplicity of 3, which is odd, so it'll cross at 3. So it's going to cross at 3. And here the multiplicity is even, so it's going to touch at 1/2. Okay, and we know that we're going to have an x to the 5th with a -4. So our leading term is going to be -4x to the 5th. Okay, and so this will be our leading term. Leading coefficient's negative, and it's x to the 5th. So we know it's in behavior. It's going to be on the left side. It's going to be going up. On the right side, it's going to be going down. Okay, and we know that it touches at 1/2. So let's say this is 1/2 right here, or -1/2. At -1/2 should be negative. It's going to touch right here, and then it's going to cross over here at 3. Come up and cross at 3, something like that. Now, you could have other humps in between here. You could have it do something like that. Although, in this case, it won't, because these are only, yeah. So it's not going to do that in this case. But I'm just saying, we don't know what happens here quite yet because we don't have the tools. It won't actually do these triple hump here, but it could in other examples. Because a triple hump would give you 4 humps, and you have x to the 5th. So you could have 4 humps on an x to the 5th. Okay, so that's multiplicity, how we can use it. Okay. So now let's talk about strategies for graphing. So our strategies for graphing. Okay, number 1, find the leading term. Okay, to identify the end behavior. All right, that's step 1. So find your leading term to find the end behavior. Step 2, find the intercepts on the x-axis. Okay, and then look at the multiplicity of those intercepts. So how do you find the intercepts? Well, you factor. You're going to factor and set it equal to 0. Okay, factor set equals 0. Multiplicity has to do with the factor occurs more than once. Then it has multiplicity greater than 1. Like an example up here, multiplicity of 2, multiplicity of 3. Okay. Step 3, which we really haven't done much with, is just find the y-intercept. Y-intercept, you find it by just setting the function equal to 0, plugging 0 into the function. So an example here, if we plug 0 in to the function, it would be -1/4 times 1/2 squared. So it would be -1/4 divided by 4, and then multiplied by a +9. So it would be 9. A -9 would be your y-intercept on this guy. Is that right? No, it's going to be +9 because this cubed is going to be negative. I'm completely goofing up here. Okay, let's just do it here on the side. So we plug 0 into here, it'd be -4, 0 plus 1/2 squared, 0 minus 3 cubed. So -4, 1/2 squared is 1/4. And then negative 3 cubed, this is where my mistake is negative 27. Here, those cancel, the negatives cancel, and you end up with positive 27. So the y-intercept in here is 27, not negative 9. My bad. Okay, so that's how you'd find the y-intercept. So that's step 3. Step 4, let's look at symmetry. And this is something, and this is if applicable. This is something we talked about, I forget when it was, a couple weeks ago, talking about symmetry. It has to do with whether a function's even or odd. So if a function is even, means all the terms have even power, then it's symmetric with respect to the y-axis. So an even function is symmetric with respect to the y-axis. And then we also have odd functions. Odd functions meaning all the terms in the function are odd. Then it's symmetric with respect to the origin. So this is with the origin. And we talked about that last time. And the 5th step is always remember the maximum number of turning points is one less than your leading exponent. Okay, so let's look at an example here. Okay, so here is polynomial. We know that this polynomial has the leading coefficient, the leading term. Leading term is even, the leading coefficient's a 1, so we know the end behavior is going to be going up on both ends because it's an even leading term where the coefficient's greater than 0. So that is, we did step 1. We found the end behavior. Now, let's factor it, okay? So factor this. Well, you're going to factor this by using a U substitution trick, okay? And what we're going to do is we're going to set U equal to x squared, and then you'll end up with U squared minus 2U plus 1. This is fairly easy. It's one of the ones you have memorized. It should be U minus 1 and U minus 1, okay? Then we're going to substitute in our x squared. Okay, and then this is a difference of squares. So we also have this one memorized, the formula memorized. So we can factor those. And I'm going to group them because notice these are alike and these are alike. So it's x plus 1 squared, x minus 1 squared. Okay, so we know this factors into this. And we know that it touches here because these are both multiplicity of 2, which is an even. So anytime the multiplicity is even, it touches, it doesn't cross. So we know it touches at -1 for this guy and +1 for this guy. So we know here at -1 and +1, it's touching. And we know it's going up, so it's going to come down, it's going to touch on this end, and over here, it's coming from this direction. It's touching, and it's going up that direction. Okay, now that's finding the intercepts. Now to find the y-intercept, just plug x equals to 0. Okay, if we plug x equal to 0 into this, so what's f of 0? And that will give us, if we look here, 0 here, 0 here, these are wiped out, all we're left with is 1. So we know at 0 here, it's gonna cross at 1 on the y up here somewhere. We don't know, however, if this is gonna be our max, relative max. It could. This could be your point, or maybe it's over here, or maybe it's over here. And we won't figure out those tools until we get to calculus. But we can hypothesize it's gonna look something like this. Okay, so that's how you use those steps. Okay, and we know since it's 4, it's gonna have a max of 3 turns. And here's 3 turns. All right, so I look forward to seeing you next time. That's the end of this lecture. Make sure you work on your homework on the sections and keep up with your work while we go through this experiment. Thank you very much.